Hello everyone, we are Group 68 and today we are excited to present our work titled Detection Transformer for Pedestrian Detection in Autonomous Vehicles. This project was conducted as a part of Neural Networks and Deep Learning course and is being presented at a Machine Learning Student Symposium 2025. Pedestrian detection plays a key role in development of safe autonomous vehicles and our project explores the use of transformer-based deep learning models to tackle this problem. Let's dive into the motivation behind this work. Pedestrian detection is a core safely feature in autonomous vehicles, helping them understand and respond to dynamic environments they operate in. Accurate pedestrian detection is critical for preventing accidents, especially in urban settings with dense foot traffic. Many existing models struggle with edge cases like occulted or small pedestrians. Failures in detection can lead to serious consequences, including fatal accidents. Our goal is to enhance the pedestrian recognition by using a detection transformer DETR, which provides a powerful attention-based mechanism with improved detection capabilities. We aim to make autonomous navigation more reliable and safe for everyone. For our project, we curated a dataset that is specifically focuses on pedestrian annotations using the COCO format. RoboFlow was used to pre-process and manage the dataset, where we applied auto-orientation resizing to 640 by 640 pixels and split the data into 70% training, 20% validation, and 10% test. By narrowing the dataset to pedestrian-only images, we ensure that the model could specialize more effectively. The output of the model includes bounding boxes highlighting each detected pedestrian. The visual outputs allow us to validate detection accuracy and performance in real-world scenes. This structured input-output pipeline is essential for models' learning and evaluation phases. Moving towards methodology and metrics, we use a pretend DETR model with a ResNet 50 backbone. DETR reframes object detection as a set prediction task, making it more elegant and end-to-end compared to traditional models. We fine-tuned it to our pedestrian dataset to adapt its general features for our specific class. The key evaluation metric we use was intersection over union IOU, which measures how well the predicted bounding boxes match the ground truth. We also tracked average precision, F1 score, and recall to understand the detection quality from multiple perspectives. These metrics give a comprehensive picture of both the model's precision and its ability to detect or relevant objects. Our baseline model was a DETR. So DETR is a unique because it eliminates the need of components like anchor boxes and non-max suppression. Instead, it uses a transformer-based encoder-decoder architecture. The encoder receives image features extracted by ResNet 50 and models global context using self-attention. This is especially useful for detecting pedestrians of varying sizes and visibility. The decoder works with a fixed set of learned object queries, predicting bounding boxes and class labels directly. Positional encodings help the transformer understand spatial relationships within the image. Finally, the decoder output is passed through a feed-forward network to produce final prediction. This approach simplifies object detection while boosting robustness of the model. Moving towards optimization and fine-tuning, we began with a pre-trained DETR checkpoint and fine-tuned it for pedestrian detection. We used the Adam optimizer with a learning rate of 1 e raised to minus 4 to ensure efficient convergence. The ResNet 50 backbone was fine-tuned with the same rate but with stability in mind due to its pre-trained status. To avoid overfitting, we applied weight decay of 1 raised to minus 4. We trained the model for 100 epochs, during which we observed steady convergence with a final loss dropping of 0.02. Additionally, we placed the original classification head with a new one to predict only one class pedestrians. This made the model more task specific and improved both accuracy and training efficiency. Here is the code that we use to fine-tune the DETR model using PyTorch Lite module. Now, let us move towards the next slide, that is evaluation and comparison. Our fine-tuned model was evaluated on 10% test and was kept completely unseen before training. It achieved a mean average precision of 0.53 and mean average recall of 0.57 using IOU thresholds ranging from 0.5 to 0.95. This is a strong result, especially considering the base DTR model without fine-tuning only achieved a MAP of 0.4. This represents a 20% improvement in detection performance after fine-tuning, which clearly shows the benefit of tailoring a model to specific domain. It also highlights DTR ability to smaller focused datasets. Now here is the evaluation results of our experiment where we tracked average precision and recall using COCO evaluator. The slide shows a side-by-side comparison between input image and the ground bounding boxes and prediction for our fine-tuned model. As we can see, the bounding boxes closely match the annotated positions of pedestrian. The model successfully detects pedestrians in complex environments with varying positions and levels of visibility. The kind of visual validation is crucial for real-world applications, where detection must be accurate under unpredictable conditions. Now let's move to our results. Here we provide more examples showcasing the robustness of our model, where it's day or night, crowded or sparse. Here is our prior work. So our prior work focused on foundational deep learning models, including MLPs and CNN. This helps us understand core concepts in image classification and detection. Building on that, we explored DTR model, which is based on transformers. Here are some of the references, and thank you.